So I want to tell you about the mathematical journey I went on after my first encounter with this problem. The problem itself is about using this inequality involving floor functions to prove this complicated looking thing involving factorials. For today's video though, we're ignoring the factorial side of things and only playing with the floor functions. The floor function, which formally uses these lower brackets, denotes the largest integer smaller than or equal to its content. For example, the floor of 1.93 is 1, and the floor of negative 1.93 is negative 2. We also have the ceiling function, which denotes the smallest integer larger than or equal to its content. Both the floor and the ceiling of an integer is always itself. The right side of this inequality from the problem looks a bit like a rearranged linear combination of the left side. Except instead of having 5 things in each floor function, we now have 4. Now intuitively, this will make the right side less than the left side in general. And it's interesting to see if there are strange exceptions because of interactions with floor functions. But I decided to take a turn down the path of the linear combinations adding to the same number of things. I started out with the simple case of trying to map out all possible values of the floor of 2x plus the floor of 2y, where x and y are between 0 and 1. Next is what happens if I move an x and a y between the brackets. From the floor of 2x plus the floor of 2y to the floor of x plus y plus the floor of x plus y, or 2 times the floor of x plus y when simplified. This time the graph depends on when the sum x plus y crosses the threshold to the next integer, so it ends up looking like this. Since we overlap the two graphs, we can shade the places where one is bigger than the other. Green for where floor of 2x plus floor of 2y is larger, and blue for the opposite. For the case of 3x's and 3y's, if we separate them into 2 brackets, they look like this. Now if we move an x and a y between the brackets, we get the floor of 2x plus y plus the floor of 2y plus x. The graph takes a bit more thinking to draw. Notice how the boundaries between the values become where 2x plus y and 2y plus x are integers. That gives us these slanted lines that are still crisscrossed. If we stare at the overlapping graphs long enough, it looks almost like we squished it until the lines were tilted. Now if we move a bit more of the x's and y's between the brackets until they're equal, we have 1.5x and 1.5y in each bracket, or 2 times the floor of 1.5x plus 1.5y, for short. The graph looks like the vertical lines and the horizontal lines were so tilted that they line up with each other. We can technically do this for any combination between the brackets, with messy fractions or decimals or even irrational numbers. And the lines will end up somewhere between the first and the last cases. So what about the regions that are left out? Is it just impossible to have linear combinations of 3x's and 3y's that would end up with lines like these? Turns out we can have lines like these. We just need to have negative coefficients inside the brackets, because these lines have positive slope. Math makes sense again. Now that we figured out the case for 3x's and 3y's, generalizing to the case of n x's and n y's should just be a matter of patience and time. And if we know what the graph looks like for any linear combination of n x's and y's in 2 flooring brackets, does that mean we can also have a general formula for when 2 of these linear combinations are the same value? Or where one is greater than the other? Let me know what you think in the comments below, and until next time, stay curious.